So today I'm going to tell you a little bit about declarative machine learning systems, which is like a new trend, let's say a new paradigm for building machine learning solutions. And I will give you a little bit of an examples through the use of Ludwig, which is the declarative machine system that I built, and also some examples from Predibase, which is the company that I founded that uses Ludwig as its foundation, but builds on top of it with additional pieces of tooling. And I have a lot of material. Maybe I will not cover all of it. Happy to take questions and discuss it further after the presentation if you're interested. So already, I'll already give a presentation about me. And so the, let's say, provocative thought, if you want, that I will start with is that in enterprise in particular, machine learning, there's kind of a false dichotomy of building systems either by relying on low-level APIs like your usual suspects, TensorFlow, PyTorch, scikit-learn, or to use AutoML solutions like DataRobot, Ritual, or Google AutoML and things like that. And the idea of declarative machine learning systems is that you can marry those two approaches and get the best of both worlds. And the reason why you may want to do that is that both these solutions have some drawbacks. In particular, if you start from, let's say, a low-level API, you have the advantage of full flexibility. And here you can see like an example of a machine learning development process. Many different companies may do it differently, but this is like something generally accepted, I would say. And the advantage is that you have flexibility, but the disadvantage is that on one hand, you have to do it yourself, which means you need to hire experts for doing it. And also, there's the solutions that you build usually are bespoke and not reusable and create a lot of technical debt. This was, for instance, my experience when I was at Uber. I was developing multiple systems. Each of them was a different code base with different requirements, different tasks, different everything, really. And each of them required many months to develop and many months to deploy. And that became kind of a bottleneck for the whole organization. And so because of that, that was one of the main motivations for then starting Ludwig and starting building a declarative machine learning system. On the other hand, AutoML solutions simplify the process and makes it substantially more efficient and simple, but at the cost of, on one hand, some black box aspects. So you cannot really interact with the system and build exactly what you want. The system builds what it wants to a certain extent. And also the fact that it's kind of a dead end. If you don't get a model that is good enough for your requirements, you are basically out of luck. And that's the reason why there's customer churn from these technologies. And so this is an example, like a quote from this paper, which I suggested, if you don't know it, it's a really good read called Waiter to AutoML, where basically users were telling the authors that whenever there is like a situation where the machine learning model that the AutoML system was training was not good enough, they switched back to manual mode and building their own things. So that was the main problem. And so again, with declarative machine learning systems, we try to marry the flexibility of a low-level API with the simplicity of an AutoML solution by providing a higher level abstraction, really. And in practice, what do they look like? So instead of defining writing all the code for describing every single piece of your infrastructure and your modeling and your preprocessing and every single aspect of your machine learning pipelines, you just define the what you want to predict or recommend or classify, and instead of specifying the how. And the what is provided by a configuration, which is declarative in nature. And if you're familiar with Terraform, for instance, a similar concept is what we're trying to apply to machine learning. And again, it's nothing new, really, in general. The separation of interest they may want between like a system developer that works on the low-level aspects of a platform or a tool and like a more higher-level user that actually doesn't need to know all the details of what's underneath is pretty common in software. You can see it in like database management systems, or you can see it like in compilers, for instance, where you have like development of the low level is decoupled from the usage at the top level by a pretty clear interface. And so the same approach is what we're trying to do through machine learning, really, with low-level development that can be done by experts and higher level usage, which can be done by users that don't need to know all the details and all the nitty-gritty aspects of building the underlying machine learning infrastructure and machine learning models. And so these are three systems that are examples of this trend. The first one is Overton, was developed at Apple. It was an internal system and was used for training many models. And basically, there's, I think, it serves like billions of queries. Models trained with Overton serves billions of queries at Apple. Looper is a system that was developed at Meta, also is an internal tool. And I think it serves, now this number is not super updated, it's probably like more than 1,000 models in production. And then there's Ludwig, which is the system that I built when I was at Uber. The main difference with respect to, all these systems have a lot in common. The main difference is that Ludwig is open source. So you can go there and use it and give it a try if you want. And so let's look at an example of how it looks like to do model development with declarative machine learning. And let's assume that our goal is to build a text classification system with data that looks like this. This is the aging news data set, if you're familiar with it, where you have both a title, a description, and a label, which is the class that you want to predict, really. All these systems work on many different types of data, and in particular, Ludwig works with images, works with audio, works with tabular data, and any mixed modalities, and can also do multitask learning. So this example is like let's say a smaller subset of what Ludwig can do, but it's like a good example for illustrative purposes. And so really all you need to specify if you want to train a model, and not only training a model, but basically building an entire pipeline from pre-processing to evaluation and deployment using Ludwig, all you have to do is to specify a configuration file that contains a list of input features, in this case, 2 elements. One is for the title and the other one for the description, both of them with a data type, because depending on the data type, the system decides what pre-processing to do and what pieces of models to actually use for training. And what is the output? In this case, the label of type category. And again, depending on the type, in this case category, different tasks may be performed. In this case, multi-class classification. But if you specify number, then it's going to be like a regression problem. If you specify set, it's going to be a multi-label classification, and so on. So this is basically all you need to specify. And then all of this is built for you. So both the pre-processing, the model building itself, the training, the model evaluation, and the deployment piece. And the data, starting from the beginning, from the data preprocessing piece, you can connect with all sort of data sources, if you want, both structured and unstructured. And you can do pre-processing directly in the system by specifying an additional piece of the configuration. So for instance, here, we're specifying how to do the tokenization of the text and for the 2 input text features. And for the output feature, we're specifying how to handle the missing values. Here, specifically, we're saying that we don't want to, we want to discard the data points that don't contain output labels, really. Here, this is just a little example, but there's hundreds of different parameters that you can change, and you can basically customize your own pre-processing the way you want, depending on the data type. For text, for images, there's all sorts of different parameters that you can change and modify. And then regarding the model building piece, this is an example of code, of PyTorch code for building an LSTM. It seems like it's actually relatively short amount of code for building the LSTM itself, but there's a lot of other pieces of code that if you were to build a model in PyTorch, in raw PyTorch, if you want, directly writing PyTorch, you will have to build too. So you have to build, for instance, a training loop, and then you will have to build like a system for saving the checkpoints of your models. And then you will have to build the data processing components. And so it's not only that specific LSTM piece, it's actually a lot of code that you have to write. How you would go and do it in Ludwig specifically? Well, you basically just specify the encoder section in the configuration, and you can say that you want to encode the text using an RNN encoder using an LSTM cell. This is all you have to specify, and you will get that implementation for free. And also for this, there's many, many different types of encoders, from simple CNNs to LSTMs to transformers and pre-trained models. All of that is basically one string away from you to use it. And once you have this configuration file, you can basically just run Ludwig train, specifying the dataset that you want to train it on, and the configuration and the path to the configuration file. This is all you have to do for training a model. And then you want to evaluate a model. This is also, again, an example of how you would go and potentially take write the code for doing it yourself. But the Declarative Machine Learning System helps you also by also providing you mechanisms for evaluating and visualizing the data the predictions that are coming from the models. And here is an example of one of the, I think, more than 30 already baked in visualizations that are available. This one shows the confusion matrix of the model on the test set. Again, there's 20 more of those, so you have a lot of flexibility there. Another big advantage of a system like this is that you can very quickly iterate on models. You can basically keep your configuration fixed and change just little pieces to basically modify every single aspect of your pipeline. And for instance, let's assume that you don't want to use an LSTM, but you want to use BERT. All you have to do is to change the encoder specification to be of type BERT instead of being type RNN. And that's all you have to do, and now you have like a new model, which is a BERT-based model. Or let's assume that you have a lot of data, and so you don't want to use a pre-trained BERT model, but you want to train a BERT architecture from scratch. And you can specify the parameters of the BERT architecture. Basically, every single architecture, every single model that is available has all the parameters that you may imagine for defining the actual architecture that is trained. So you have a lot of flexibility for that. And you have also flexibility with respect to how the models are trained. So you have a training section that contains all sorts of things like learning rate, regularization, which optimizer to use, which learning schedule for the learning rate do you want to use. So you have full control. There's more than 500 different parameters that you can change, and the documentation is extensive. Once you train your model, you want to serve it, you just have to basically call Ludwig serve and the path to the model that is trained. And basically, it spawns a REST API that you can query. This is an example of a query using curl. All right, so just to summarize, an approach that uses a configuration system like Ludwig has many advantages. The first one is it's really easy to start. You don't have to write low-level machine learning code if you don't want to. And basically, you have a readable and shareable configuration that you can then reuse. But you also have all sorts of deeper control that all the control that an expert may require. And the additional advantage is that it's also very easy to extend the platform. So here on the left-hand side, you see an example of how you can define your own Python classes, for instance, in this case, an additional encoder. And you just give it a name to add it to a registry through like a decorator. And once you do that, it becomes available in the configuration, and as a consequence, also in this case, in the UI that we're building on top of the configuration itself. So it's extremely simple to add a new loss, a new regularizer, a new everything really to the platform. It's really easy to extend. And the very last piece is that it also contains additional, let's say, advanced features like hyperparameter configuration still inside the configuration system, and distributed training out of the box, and also state-of-the-art models. And basically at Predibase, what we're doing is using this like a central piece of Ludwig, making it possible for enterprises to connect data, train models in this declarative way, managing the models in their life cycle, evaluation, tracking, and iteration, deploying them as either for real-time deployments or for batch inference. We do both of them. Abstracting away the complexity of running your own compute and machine learning infrastructure by a layer that works on top of all major virtual private clouds. and also providing different interfaces for different kinds of users. A Python SDK for more expert users, a graphical user interface, and also this new concept which we call PQL, which is a declarative extension of SQL for doing machine learning. And so these are some examples. This is, for instance, the command line that we've seen before with Ludwig. This is the Python SDK, where we basically have one line for connecting data, one line for creating a model, one line for training it, one line for predicting, and one line for deploying. As simple as that. You also have a graphical user interface where you have like an abstracted presentation of your models, and you can drag and drop and modify them interactively. And then there is this extension of SQL, which we call PQL, which adds predicates for both training model in a declarative way and also using those models for obtaining predictions. Here, for instance, assuming that we have a model for predicting the label from the dataset that we have trained in the previous example, you can say selecting the title and body from the article table where some clauses, like in this case, the label is null and the date of the article is later than a certain date, and then you can predict the label directly from SQL. And this is super useful for users that may know how to use SQL, but may not know how to train a deep learning model for a task like this. The advantage also of using a configuration-based system is that then it becomes very easy to do version control. What you're doing the version control of is actually the configuration. You have artifacts associated with the configuration after training, but you're version controlling the configuration, and so you can really see that from a version to another, for instance, you just change the learning rate, and you have a better performance. And then you can have all the lineage. So this is a screenshot from the Predibase deployment of an actual, we call them model repos similar to what people do with Git, really. And so we have all the tracking that Git enables you. And so in summary, there are like a few aspects of the model development with a declarative machine learning system that are important in my mind. The first one is that it's very modular and reusable, and so the advantage is that you can have a plug-and-play architecture, so you can extend the system very easily. The other one is that you have state-of-the-art performance without having to reinvent the wheel every single time. You also unblocks version control in a way that is very, very nice and delightful to use. It's reproducible, which is very important for everyone working machine learning in enterprises. And it's also really debuggable. I haven't shown you an example, but it's very easy to debug. And finally, the separation of interest concept is very important, in particular in organizations where there's multiple personas working together in a team towards building a machine learning solution. And for scaling up something like this, what we have done in Ludwig specifically, we've made it so that we integrated with Ray. And so every single thing that you do in Ludwig, every single configuration that you specify in Ludwig can be run on multiple machines in a Ray cluster very easily. And here you can see on the right-hand side is the difference between a configuration that runs locally and on the right-hand side, on the left-hand side, and on the right-hand side, you can see a configuration that runs on a Ray cluster, in this case, using resources like on 4 machines in parallel using GPUs. And the same is true also for hyperparameter optimization. We basically use RayTune for running all the jobs in parallel on a cluster, and that makes hyperparameter optimization basically extremely simple to do in Ludwig. The very last thing that I wanted to touch upon is the idea that adopting a declarative machine learning solution in your organization is very compelling in my mind because of several reasons. In particular, the fact that there's value for many different stakeholders across the organization. And so in my experience, but that is true, I believe, in most enterprises, there's not only a data scientist that builds the models, not only a machine learning engineer that usually puts them into production, not only like data analysts actually use these models, or also developers, product developers that use the models after they're deployed. All of these people collaborate together to obtain the final goal of putting a machine learning project in production. And so for domain experts, the advantage is that they can build machine learning models without being machine learning experts. They need to be domain experts. And for data analysts, they can do predictive analytics without, again, knowing about the intricacies of developing machine learning models and the infrastructure aspects behind it. For data scientists, they have reusable components that can swap in and out, and they don't have to think about the infrastructure complexity. And for machine learning engineers, it's very easy to do scaling and deployment with a platform like this. And finally, for business leaders, there is like a reduction in time to value, which increases the return of investment that they will put into doing machine learning. So I believe it's kind of a win-win proposition. And so that's it. I wanted to trying to leave time for questions. And if you want to get in touch, please reach out to me. There's also a lot of material available online. Again, Ludwig is open source, so please go there, try it out. And if you want to talk more about Predibase, I'm here also for the rest of the day. Thank you very much. So I'm a little bit blinded by the lights, so I cannot really see if there's people that want to ask questions, but hopefully, if there's anyone, that there's a mic, I think, around.
Hello? Yeah. Okay, thank you. Thank you very much. So this is great. If like, I may ask a challenging question, but what would be the one reason your users or customers would not want to adopt your, what is the shortcoming of it, if there is any?
Yeah, so I think there's a couple aspects. One aspect is there are some, let's say, problems that involve broader outer loop, if you want, in particular for data collection and interaction. So for instance, if you want to do reinforcement learning and you have an environment, you need to interact with the environment and the model part and the environment part and the data part are all kind of really tagged together. And there's no notion of environment and there's no notion of data collection. The data collection here comes from like a data source directly, right? And so for instance, for those kind of use cases, I would not recommend like a system like this at the moment. I think that there could be like a potentially valuable declarative system for reinforcement learning, but it's something that right now is not there, to the best of my knowledge. But this is the state of things right now. And then the other aspect is there is I would say most machine learning cases are covered by the different tasks that depend on the output feature data types. There could be some cases that are not covered. So there's a long tail of machine learning cases in the world, I would say. Obviously, a tool like this works really well for the fat part of the tail. The long part of the tail, obviously, bespoke solutions may be the best choice for the long part of the tail. Is there another question?
Yep. Sorry. Thank you for the. I quite like the declarative part of the demo and then the session. But my experience so far with configurations are not so great. Particularly interesting in that versioning, because often what I find is not only the configuration themselves, the YAML files needs to be versioned, but also the underlying library that's kind of consuming that also keeps evolving too fast. That means you have two versions to match, like the part that's going to parse your configuration and the configuration itself. How do you keep that thing in sync and contained?
Yeah. So all the information needed to replicate what happened in a specific run is contained in the outputs that are saved along the way, including, for instance, the freezing of the libraries that were dependent on that. So it's really easy to replicate exactly everything that happened at every single, including the version of Python that was used for training. So you can replicate it 100% in Ludwig. And the nice thing about Predibase, for instance, is that you don't have even to think about that. We take care of all of it. It comes. It's kind of completely transparent to the user. The user can look at that if they want to, but it's not. They don't need to manage it at all.
Hi. question about the serving on Predibase. Like, do you have...
Sorry, I cannot hear you really well. Can you speak louder, please?
Oh yeah, I have a question about the serving system in Predibase. Do you have stuff like metrics or looking at feature drift, for example, all those concerns? Is it there in your serving system?
Yeah, so when models are trained, everything that happens during training is tracked, so you see all the learning curves and all the performances, etc. And after a model is deployed, again, deployment is like a click of a button, you can specify which engine you want to run it on, and engine here means something similar to warehouses in a data warehouse, so you specify how many machines and what type of machines you want to deploy it on, and it is deployed. In terms of features for tracking after the deployment, right now there's a bunch of things that we track and make automatic, like for instance, retraining and retraining triggered depending on like either time or performance or things like that. And the drift specifically, it's not something we're tracking yet, but it's a feature that is coming out in the near future. But again, it is a matter of, if you want, what is the most, in our experience, the most useful thing for retraining. So, the main reason why you may want to detect drift is obviously, you want to understand what's going on. On the other hand, is because you may want to retrain a model on top of it. In our experience, in most cases, you would do an out-of-time retraining anyway, and so that's the first feature that we added to the platform. Now, also drift as a trigger for retraining is the next feature that we're going to add really soon.
Thank you.